So our last talk is from Praveen and Sherlock from Microsoft. So these are the people ported RocksDB to Windows for the whole community to use. So let's welcome Praveen and Sherlock.
Thanks a lot. So I'm Praveen from Microsoft. I work in Bing infrastructure, and Dmitri and Sherlock are my teammates, and we built this thing where we integrated RocksDB into something called ObjectStore, which is our online data serving platform. So I'll talk about broadly three things. Porting RocksDB to Windows, then plugging it into ObjectStore, and then using it for a large-scale service. We got interested into RocksDB because we had experience with LevelDB, which we had used in some projects. And so RocksDB was a natural choice as a much improved LevelDB. And the other motivation was providing a storage engine with different characteristics for our distributed online serving platform. And some of those motivations would be clearer further down. For porting it to Windows, we implemented the port interface that RocksDB exposes, and that's how I guess a lot of open source softwares do. And we clean up the code where the code was directly using Linux APIs, say, as opposed to using the port interface. While porting, we had to take care of the operating system differences, definitely in our port code. In some cases, the APIs don't map directly from Linux to Windows, so we tried to simulate them and provide some close approximations which work correctly. We also had to take care of compiler differences because RocksDB uses a lot of features from C++11, which is great, but not all of them were supported by our MSVC compiler at the time, or they work a little differently, so we had to work around those things. And last but not the least, we had to make sure all the tests pass on Windows, and that also took some effort. So code porting alone is not sufficient. If we start to support a new platform, we have to think about build an integration story. So we used AppWare as our continuous integration platform, and RocksDB team was gracious enough to add it to the build pipeline. So now, for example, if you submit a pull request, Travis does the build for Linux, and AppWare would do the build for Windows to make sure Windows port also keeps working, similar to the Linux system. And of course, we had to integrate with our internal build system. Now, to talk about integrating it with ObjectStore, I'll provide some brief overview of ObjectStore itself. So it's, as I mentioned, it's an online data serving platform in Bing. It supports hundreds of applications with very high throughput and very low latencies. Latencies are in a few milliseconds. And also predictability of those latencies is also an emphasis point. It supports pluggable storage engines, which is what allowed us to plug in RocksDB as a storage engine. For example, if you look at the diagram here, it shows the DiskStore, which is the current storage engine, and it supports something called a local store interface through which it can plug into rest of the ObjectStore infrastructure. So to support RocksDB, we had to implement this local store interface. And ObjectStore, of course, provides the replication, partitioning, and distributed access on top of the local storage engine. Table in ObjectStore, similar to, I guess, a lot of other systems, consists of a number of partitions, number of logical partitions. And these logical, so any given node would host a number of tables and a number of partitions from different tables. And these partitions can even be coming from different storage engines. For example, here I show table 1 to 3 coming from RocksDB store versus table 4 to 6 coming from DiskStore, which was the original storage engine. And here I show a single box, but of course, same table would typically have multiple partitions. And they all run in this same table server process. And this is what I just talked about. With that comes the need for provisioning. So we need tight controls on what resources each partition uses. So ObjectStore requires each storage engine, or in fact for us to specify for a specific partition how much memory, disk space, and other resources like IOPS and network usage we are going to do, so that it can then manage how these can be hosted on a particular server and also redistribute them as needed. The replication system ObjectStore has is a primary-based replication, and it has eventual consistency, so essentially async replication. It has a memory log, which is a circular buffer which holds the recent writes, which is backed by disk log, which is its transaction log, which is then backed, of course, by the persistent store, which is the storage engine itself. And interestingly, new writes actually go to the storage engine first, and then a memory log gets a slot reserved but not committed, and then they go to storage engine. If storage engine is able to persist that, then that slot is committed, and memory log is periodically flushed to disk log. Now, to provide some background on the motivation of using RocksDB, I would give a brief overview of the current storage engine, which is DiskStore. Its implementation is based on FlashStore, which was a research paper published by Microsoft Research. And in really brief, it uses a circular file, so all the data is contained between head and tail. And as the new writes, updates, and deletes come in, they get written to the head. And as this space grows, you can imagine updates to the same records and deletions that need to be cleaned up. So garbage collection is periodically run, which starts from tail, and it determines whether a particular record is still valid. If it's still valid, it gets written to head just like any other write. And if it's not valid, then tail just moves forward. So it has almost all or most of the index in memory. So writes are very fast because they are log structured, as you can see, and reads are very fast because we have index in memory. So if we ignore the caching, then it knows the exact location or exact offset in the circular file of any particular key. So it can just go and fetch it in a single read. So that's the fastest you can do if you ignore the caching part. Now, compared to that, RocksDB's index is at block level, and typically many records can fit in a block. So we can cut down on the memory used by index significantly, and thereby we cut down the number of servers needed to serve a particular application. It does increase the read latency a little bit, because in case of RocksDB, the reads can go to multiple files, even with Bloom filters and everything. And in general, with RocksDB also tends to have higher read and write amplification. For DiskStore, I've heard read and write amplification less than 4 or 5, while it can be higher with RocksDB. So we can sacrifice a little bit of read latency, but we can gain a lot in, say, saving the memory and saving the number of servers. So for applications which can tolerate that, we can provide this as a storage engine option. To integrate RocksDB into ObjectStore, we had to implement the local store interface I had talked about. We had to integrate with ObjectStore Replication and a few other things I would talk about. So to integrate with Replication, apart from other things like implementing the right interfaces, one thing the storage engine needs to do is provide something called an RSN, which is the record sequence number it is at when it starts up, so that the replication system knows how far behind it is, if at all, and then catch it up using either the local disk log or from remote replicas if it's really far behind. So unlike the previous talk, we chose to map RocksDB sequence number to our RSN because it was probably more cumbersome and more impactful to change the current system to plug in RocksDB sequence number. And the way we do it is, if the wall is on, then we just save the last RSN into the new record, and we use put log data for that. If wall is off, which is what we do actually in our configuration, and I would talk about that, then I can illustrate what happens. So let's say these are the sequence numbers. That's the ObjectStore RSN, and this is the RocksDB sequence number. When a mem table becomes immutable, and we added a callback for that called onMemTable sealed, we save this mapping of the current object store, RSN, and RocksDB sequence number into an in-memory map. And these I show moving in the lockstep, which is not necessary, but this is just for illustration. When this mem table is eventually flushed to the SST file, you can imagine the sequence numbers have already moved forward. But what we persisted is for an earlier sequence number. So what we do is look up the sequence number corresponding to this SST file in our map, and then we find that, oh, this SST file had 1, 2, 3 as the RocksDB sequence number, so the corresponding RSN is 1002. That means that data is persisted. So we write a latest RSN file, something called a latest RSN file, which saves this RSN, which can be queried on recovery, and then we remove this mapping. Now, as I had mentioned, provisioning is very important with the kind of multi-tenancy we have. So we created formulas for memory usage, disk usage, and we monitor that RocksDB usage remains within them. One interesting thing we needed to think about was that we use different storage engines, and they use different allocators. For RocksDB, we are using JMalloc as the allocator, and the current DiskStore uses a custom Windows heap instance for the allocator for each partition. So for provisioning, we need to make sure that a partition takes only a certain amount of memory. But another important thing is when that partition is removed from the node, that memory should be returned not just to the allocator, but all the way to the operating system, so that another allocator could use it, or even a different process or different service can use it. So for example, here, let's say the RocksDB store, this partition goes away. The memory is reclaimed to JMalloc, but we want to make sure that that gets reclaimed all the way to the operating system, so that when the new partition comes in, which could be DiskStore, which is going to ask for a Windows heap instance, it is going to ask operating system for the memory. So for that consideration, this is what I just talked about. We had to think about what happens with different allocations. So if we have sub-page allocations from different partitions, they can get mixed in a single page. So let's say if one partition moves away, that whole page cannot be reclaimed by the operating system. If we have page granularity allocations, then JMalloc does free individual pages to OS, and of course it does in a smart way. It tries to coalesce the ranges and tries to do in a performant way. So fortunately, most of the large allocations in RocksDB are at page granularity. Memtable works through an arena, and block cache, by definition, or is typically page aligned, or has multiples of pages. And of course, we have our internal allocations also for the layers above RocksDB. So to really make sure, we also evaluated JMalloc custom arenas, where what we can do is allocate a specific arena for a specific partition. And when that partition is removed, we get rid of that whole arena. So that ensures that all the memory is reclaimed, and also deallocation is done in a performant way. And we were evaluating both these approaches. There were not really stark differences, but still the custom arena provides more predictability, and it provides better performance. So that's probably what we would end up going with. The downside with that was the programming model is a little bit harder, and of course it introduces complexity. So what we do is we switch the arena whenever a thread starts to do work on behalf of a particular partition. So through a public interface, or if any thread pool work any work item from the thread pool that needs to be done for a particular partition, we switch to that arena. So in future, it would be great, and that's a feature request for RocksDB, if RocksDB can accept allocators for large objects, and then in that case, we can just provide a custom arena as the allocator for a particular partition. As one can imagine, for a large-scale service, we had to do a bunch of perf tuning. One of the things we did was we turned the wall off, partly because we already have transaction log in our replication system. But even bigger reason was it allows us to get rid of buffered I/O, and it eliminates some of the noise. And I'll talk more about the buffered I/O. We used rate limiter to smoothen some of the things like spikes due to compaction, and we did some scenario-specific optimizations, and some additional things I'll talk about. So similar to, I think, the talk earlier that there are a number of options that we can tune in RocksDB, we had to try various things and see what works best for our scenario. So this is an example where we measured the effect of block size and prefix extractor on range query perf. And our sweet spot turned out to be 8K, and the prefix extractor does help with higher percentile latencies. We also disabled OS buffering. In Windows port, I think we worked on it even earlier because ObjectStore team in general was very specific that we had to disable OS buffering, because that removes vagaries of operating system, provides more predictability, given the provisioning story I talked about, and also for the higher latencies. Especially, there are some issues with Windows. I don't know if you guys run into such issues on Linux, but with certain options on certain versions of Windows, the system cache can take large amount of active memory. And it might be thinking it's doing the right thing, but that doesn't work for server applications because some of the higher percentile latencies can then shoot up. And as I mentioned, the provisioning requires tight controls on the memory. So on the flip side, then we had to use our own buffering and tune it because we can't really have each I/O directly go to the disk. So we use a combination of buffer per request and per file. Some of this code actually got hoisted to RocksDB itself. The write buffer, I think, was added by us or along with the RocksDB team. And some of it is in Windows port where we do the buffering for read. So essentially, we have disabled buffering for almost everything, flushing, compactions, reads. It's enabled only for wall because the transaction log should go to operating system buffers immediately and not sit in the application process. On the other hand, as I mentioned, we turned the wall itself off because of this buffering. And then for small files, we left it on. And of course, monitoring is super important. So we integrated the logs and counters into our infrastructure. We redirected RocksDB log into our log. And for counters, we periodically query RocksDB and jmalloc stats and exposes our counters. And we chose a very critical and very high-scale service to migrate to this new system. Part of the reason is that provides most bang for the buck, because the biggest advantage of using RocksDB for us was reduced resource savings and improved hardware efficiency. Of course, I mean, it has additional features that we can use, but that was the initial motivation. So for this kind of service, of course, we need to make sure that we don't cause any disruption when we do the switch. ObjectStore provides the ability of live swapping a storage engine, which was really helpful to us. So we can take a live running system and then say now convert it to RocksDB. And the way it works is it's kind of similar to bootstrapping a new replica, where it would snapshot from the original engine, prepare the new engine, tear down the old engine. But in addition, it does the monitoring, how that is progressing and if it's succeeding. And if it fails, then it can roll that back. So that notwithstanding, since it's a very, very critical service, almost all Bing traffic hits it, we are keeping a standby system so that if anything goes wrong during this migration, we can still go back to we can still switch traffic to the standby system. And of course, standby system we can keep in sync with the current system. And we had to do, of course, significant full-scale testing of conversion, functionality, and performance, which is still in progress. We are still working out last kinks, and hopefully we put it in production very soon. Sample perf results, and of course, they vary, but I just took, let's say, one table and one API. With RocksDB, due to the efficient index usage, memory usage can be cut down 6 times at the cost of slight increase in read latency, which in this case was tolerable. So overall, we had a great experience with RocksDB. The code itself was very stable, very few bugs found, and it was always a pleasure to work with RocksDB team, very responsive and eager to collaborate. So it was really great. So yeah, I'm open for any questions, but please use RocksDB on Windows, and please join us if you can. Thanks for listening.
I have a question. So why do you still use JMalloc and not this Windows heap directly?
JMalloc did, so we did some benchmarking, and JMalloc did provide some better performance, and it was almost easier to integrate custom arenas through JMalloc. But yeah, it did have slightly better performance than Windows heap.
Thank you.
I didn't quite understand how you're saving memory. Like, what used to be the representation before for object?
Oh, so for ObjectStore, it's mainly the index saving. So just think of it, it's not true in absolute terms. It's not necessarily the full index, but imagine that your full key index is in memory. So let's say you have 1 million keys. So it's going to know, for every single key, it'll know the offset in the file. Versus in RocksDB, let's say we have 1 million keys, but 1,000 keys, let's say, fit in or 1,000 would be too high. Let's say 10 keys fit in a block. So now suddenly, instead of 1 million rows in the index, now you have only 100,000 rows in the index.
How do you look up the key that's not directly indexed?
That one is all with RocksDB, with RocksDB block index. So it's, the saving comes mainly from the index saving. So because the block index is at a block level, and each block can have multiple records in RocksDB.
Hi. So you mentioned about the random access file. I know you have a workaround for this. You implemented something of your own. Is there any plan to fix it in the file system, the sparse file, the memory usage?
On Windows, you mean?
Yeah.
So when I talk to Windows team, they've of course done a lot of improvements and fixes, and it keeps changing. But I think the experience, and especially this is the guidance we got from ObjectStore team, that just say no to buffer I/O. So we just were not almost allowed to use buffered I/O. And I was resistant to that earlier because I came from Windows team initially. So, but then eventually I saw cases when the memory really blew up in certain cases. And even with WAL, for example, even simple buffering is WAL, most of the times it works okay, but in certain cases, a system would take too much memory, or it would start impacting high percentile latencies. Anything else? Thanks, everyone.
Okay, thank you for coming. I think food is outside, right? Yeah, food. There will be food outside, and now there's social time. And please come next time. Thank you.